All right, any questions before we get going? All right, if you didn't see, I had several people ask if I could open the homework for one more day. So section 4.7 will be due tonight at midnight. All right, one last thing we gotta go over in terms of section 5.1. So pretty much everything we've done in the section so far is talking about this idea of area. So we can expand that idea to other quantities that don't really have specifically to do with area. So take this example here. I have the odometer on a car is broken, or should I say speedometer, or odometer, I guess. But I still want to use this information here to figure out how far the car has traveled in this 30-second time frame. So to kind of bridge this to what we've done in the past, let's look at a graph here. So I have 5-second intervals. So I have 5, 10, 15, 20, 25, 30. And basically what I'm doing for these intervals is, I don't really, this is not going to be accurate, but that's okay. I know that my speed is going to increase in some way over the first 20 seconds. And then it's going to go down a bit as I get to 30. So basically, since I'm taking my speed estimates in these 5-second bursts, I don't really have any idea of what's going on, from instant to instant. All I know is that, in this 5-second interval of the graph, I can think of this speed as 17 miles per hour. And this next interval is going to be 21. So I know that somewhere inside that little 5-second span that I knew the speed, and I'm using that speed as my sample. I'm not saying that so I know that the speed was not, for example, 21 miles per hour everywhere in that t equals 5 to t equals 10 window, but I know it was once in there, so I'm just going to assume that I had that speed the entire interval. So any questions so far about just the rationale of what I'm doing, this sampling to find an estimate? All right, so let's think about this. Just draw 1 or 2 more bars. What are the units of the x-axis in this case? Seconds. What are the units of the y-axis? Miles per hour. So I'm drawing a graph because we can think of this as an area. If I were to find an area right now, knowing that everything horizontal is measured in seconds, everything vertical is measured in miles per hour, what's that unit going to be? Something miles second per hour. So is there a better way that we can express like 17 miles per hour? What's a better way for us to think about that? Yeah, I'm gonna keep seconds. So let's convert the vertical axis. At a minimum, what change do I need to make to miles per hour? Just so I have some sense of compatibility. I can do miles per second. That's going to be a little hard to deal with because the numbers are going to be so small. Let's do feet per second. So we'll do a quick little conversion here. If I know that 1 mile per 1 hour, and I want to get to how many feet per second is that? How many feet are in a mile? 1,280 feet. How many seconds are in an hour? 60 times 60. So basically, if I multiply all of these values here by 5280, and divide by 3,600. That'll give me something in feet per second. So let's go ahead and do that first, just so we have something consistent to think about. So I get 24.6. $30.3. 34.7. 41.9. 46.2. And 44.7. And 40.4. So now we've transformed this idea. We've transformed miles per hour to feet per second. So now if I were to take this area, what kind of units would that give me? Let's just take the area of one of these rectangles. So if I were to take this first rectangle and bring it down here, what is the base length of this rectangle? 5 seconds. What's the height of this rectangle? 24.6 feet per second. So if you find the area of that, we'll call it A1, that's 24.6 feet per second times 5 seconds. So what does that come out to be, both number and units? So 24.6 times 5 will be, is that 123? 123 what? Right, 123 feet. So let's pause there for a second. So basically what I've done, just for 5 seconds, but I can do this. I can repeat this. But I know that for that first chunk of time, the car drove for 5 seconds. And I also know that somewhere, in the interval, the car was traveling 24.6 feet. So I'm going to use that to get an estimate for how much distance we covered in that chunk of time alone. Are we okay with how that's done? Any questions about what we've done so far? Go ahead. Right. And just to be clear, I don't think you meant this, but I just want to be clear. I'm not saying that at the very beginning we were going 17 miles per hour. That may be the case, but I don't know that for sure. But yeah, so how many areas do I need to get here to get this full distance? I'll ask it this way. How much time does our first area account for? So how many areas might I have to find to get? I'm going to need to get 6 of these little subintervals that all represent 5 seconds. How many speed measurements do I have? I have 7. So what does that mean I need to do? I need to disregard 1. And here's where we have some choice. We know we need to throw 1 out. I mean, there are no I think the easiest thing to do is to omit 1. Ignore 17 the right endpoints if you want to think about it that way. But when you're making an estimate, you kind of have to choose how you're going to do that. Jordan? Right. So why am I multiplying up by 5 seconds? It is not because of when it happens. It's because of how much time. So, and just to illustrate that point, if I were to take this fifth interval here, what would that be? 46.2 feet per second. So that's the speed I want. But how much time am I going to multiply that by? 5 seconds. So it's not about, when in this interval I'm measuring the speed. It's for how long am I assuming that speed is. And all people, so based on the sampling rates of this measuring device, I'm assuming that all these little subintervals are 5 seconds long. So this one would be what, 231? So any questions about how we're doing this? Can we get a final estimate to that? The distance now? So 30.3 feet per second times 5 seconds. When someone has a final estimate here, just go ahead and shout it out. But really, the thing I'm most concerned with is, are people okay with the rationale behind this, or why we're doing it? Why this gives us something of a good estimate. Sebastian? Yeah, we're neglecting that one. So we have to neglect that one. No. So why do we have to neglect one at all? So I need 6 times. So basically, I don't really have any wiggle room with that. But so I need 6 time measurements. How many speed measurements do I need? 6. That's a good question. How do we do 6? Right. So each interval, and I guess it's probably easier, it's probably more valuable to think of these intervals as, here's an interval, 3, 4, 5, 6. So you can't really distance. So we can't think of the times as being instants. We have to think of these times as being, moments, like intervals. That actually have something that it's electric also. Exactly. We could have done a right one. We could have done bad. That's about all we have. Unless anybody has a final estimate for the distance, I'm good to. Right. So any questions on that? Gabriella? The final thing, so I got the 6 distances that all come from the little 5-second intervals. How'd you get that number, Tal? So yeah, that's just the sum. So, and connecting it to Riemann sums, I'll say this: the area is equal to this sum from I equals 1 to 6 of, not area I, delta t stands for our 5 seconds, and I'll call it velocity I. So basically, I want to take a speed for all of my intervals from 1 to 6 and multiply that speed by change in time, a constant 5 seconds. So that's yeah, that's what we did.
Okay. And then you're finding the middle.
I don't think you can find a middle. I mean, if you try to do midpoints, like here's the thing about this, you don't really have access to information between those intervals, right? And like in the middle of them. So I think really you're either choosing left or right. If you want to take midpoints, then you got to say, all right, I'm going to take the average of those two numbers on either end, but that might not be. Here's the thing, with this kind of sum, you are bringing error into your life in some way. It's inescapable with this kind of exercise. All right, any questions? All right, that is all I have for you for 5.1. So in 5.2, we're going to talk more about this thing that we are calling a Riemann sum. So area is it's a very limited thing, very, very specific thing. This Riemann sum, as a more general idea, can be used for a lot more. And you just saw that with, trying to find the distance. If you know the speed that something is traveling at, you can figure out an estimate for its distance that it's traveling. So the assumption we've made so far is we're putting area under a curve. Typically positively because negative lengths don't really make a lot of sense. So when we're talking about area, we typically stick with these curves that only have positive values. But what if we had something look like this? Just because you have a curve, a function that has negative values, you can still talk about that Riemann sum. And it still works pretty much the same way. So this is an example here of 5 intervals. But look at area 3 and area 4. In my total sum, what am I doing with the area? I'm subtracting them. So if you want to think about this in terms of area, one term that gets thrown around sometimes is signed area. Because now we're allowing for this phenomenon of area, which we almost always think of as being positive. Now we can think of it as being negative depending on where it is. Another thing I want to point out here is that keep in mind what we said last time about xi star. These intervals here are they all the same width? Okay, actually, it looks like they might be different, right? So that's one thing you have a choice on in general, is how wide to make each one of your subintervals. They don't have to be the same. It's typically a smart thing to do just for the sake of simplicity, but you don't always have to make them the same width. Another thing here is, how are they choosing the X values to sample at in this example here? Or is there any logic to it that you can figure out?
Like the bases are all the same, but then it's that dotted line is different.
No, well, the dotted line is different because the dotted line shows like where I'm sampling. So basically for each one of these subintervals, what we're doing is we're choosing an X value, finding out what the function is equal to at that value, and then define the area, just assuming the function always has that Y value. But I can choose that X value however I want. It usually makes sense to be consistent and say, I'm going to go left endpoints or right endpoints or midpoints. But really, you can choose that anywhere. And when you have a Riemann sum that has these pretty wide intervals, you have kind of a lot of freedom there to choose a point you want. So any questions here about just how we're generalizing the specific idea of area to this more general Riemann sum thing? All right, so just a few like verbal details about how this thing works. Basically, what you're doing with the Riemann sum is you're taking some interval. We started calling it, this interval from A to B. And we're partitioning it. So when you make a partition of something, basically, you're dividing something into even more pieces, right? So in this case, we partitioned, or actually the thing I showed you, we partitioned it into 5 subintervals. But really, a Riemann sum can be partitioned into any number of things, any number of subintervals. In this case, we're just going to use that general n again. And then in each one of those subintervals, we are taking a sampling point. Basically, that's the value of x that we're going to assume when I evaluate the function at that x value, it represents the function everywhere inside the interval. That's kind of the rationale we use when we take a smoothly curved function and just turn it into a pile of rectangles. Then once you find those products, basically the product from you multiplying the height and the length together, the height and width, you add all those things up and you get this thing right here, which is the Riemann sum. Which this sum notation, I believe I showed you this exact thing last time, right? The only difference here is that it's not even a difference in the way I'm showing it to you. It's just kind of how now, instead of f of x star being positive, these can be negative. There's some room. So it seems like a small modification, but it's actually pretty important. Any questions so far about the changes we're making? All right. And then one word that you might be noticing here is integrals, which I'm not sure if everybody has seen before or know what that is, but basically here's what an integral is. So if I have some function defined on some interval a to b, then here's what the definite integral is. So Riemann sum is just in general the thing we showed you. You basically treat the function as how you're calling it as rectangular areas. If instead of some like finite number of rectangles, I'm interested in what happens when those rectangles get infinitely small, then I have this new thing, which is called a definite integral. So one thing I want to focus here on is this. I am wanting so like we said before, the intervals don't have to be the same width. So when I'm saying I want the largest interval to be going towards 0, how many rectangles am I trying to make? Maybe I should draw this out as best I can. So if I have some rectangles, splitting this up into intervals, but I want to start splitting these things up until, what's my goal here? How wide do I want these intervals to eventually be? Or to eventually get close to what? 0. So how many rectangles is that going to give me? An infinite number, right? So that's when a Riemann sum becomes integral. When you get to this limiting case of I have a countable amount of, some finite number of intervals, some finite number of rectangles. Now I have infinitely many. So biggest change we're making here is going from, this bringing the idea of a limit, which we talked about at the very first day of class. Now we're applying it to this area problem. This summation very old thing, goes back to the Greeks, which is why you see a Greek, basically the sigma is a Greek capital S. And Bernhard Riemann was German. So that's why that's a German S that you're seeing as the integral symbol. But you're in both cases, you're looking at a sum of a lot of things. The different context tells you which symbol and what kind of thing you're looking at. Are you looking at a finite sum, or are you looking at an integral, which adds infinitely many things together? If that limit exists, then we say f is integrable on the interval. And the theorem, if you have a function that's continuous on an interval, or it has some discontinuities, finitely many, then the f is integrable. We're not going to deal with this. We're not going to deal with functions that have discontinuities. We're going to deal with continuous functions. If you have a function that's continuous on an interval, it has to be an interval. It has to have that definite interval. Who would see this idea? So yeah, I'm not surprised it looks a little mysterious so far. We haven't done much with it, but we will very soon. Any questions so far? All right. So I have this Riemann sum. I want to partition the interval 0 pi into n intervals. And I want to find the area under the curve x cubed plus x sine x. And there's a little bit of a difference in notation here. So the way that we wrote the Riemann sum was using this limiting operator. So the limit as delta x goes to 0. In this one, I'm writing it as the limit as n goes to infinity. Are we okay with those two things being equivalent? If I have an infinite number of rectangles, that's the same as those rectangles having arbitrarily small width. I can get as close to 0 as I want. So basically, the reason I put this example in here is just to show the equivalence of these two ideas. This Riemann sum here is the same as this integral. I am integrating the function x cubed plus x sine x. I'm integrating it with respect to x, and I'm integrating it over the interval 0 to pi. So just a concrete example of that Riemann sums and definite integrals. These two things. So the thing that I put in the bullet of that slide and this integral that I just wrote out, these are the same exact thing. By definition, when you limit a Riemann sum, or you try to find the limit of a Riemann sum as its subintervals get arbitrarily small, that's when you're looking at a definite. Any questions about how those two things are related? There's a lot of things to keep track of in that notation, but we'll keep practicing. All right, moving on. So, some important relationships to look at here. The top three up there, you can, if you're interested in finding the proofs, they exist out there. They're, like I said last time, they're not things that are terribly difficult. all the time. And I'd rather spend our time. But as we calculate some of these intervals, those things are become very useful. But we can talk about these bottom three. So if C is a constant in this fourth one down, think about what a Riemann sum is. I'm going to add up how many things in that fourth Riemann sum. How many terms am I going to add? What if this was, for example, I equals 1 to 30? And I was going to add a bunch of fives together. So I'm going to add the number 5 to itself how many times? 30, right? So without even having to, so hopefully you're thinking that you wouldn't even do that addition. You could do it something, you could do it a lot more efficiently, right? What is this sum equal to? Right, 30 times 5, which is 150. So if I can generalize that, how many times am I going to add C plus C plus C? How many times am I going to do that? N times. So what is this sum equal to? N times C. What if that constant is being multiplied by something that varies? So in that case, this constant here is just, I am multiplying it by each one of my terms. Doesn't matter if I multiply before I add them all together or if I add all the terms together and then multiply. So when you have that multiplied constant, and if you'll think back to the way we did area, we could have done this too. Think back to that car example. I could have added together all my speeds and then multiplied them by 5 to get a total distance. How do you think this last one behaves? If I'm adding these two areas together like this, or subtracting two areas, is there a way for me to split this up? And yeah, there is. I can just take each one of these sums independently. So hopefully you're seeing some parallels between limit laws we've done in the past. Now we're applying those same kind of rationale to Riemann sums. If I want to find the sum of two Riemann sums, I can just bring those together or do them separately, however you want to think about it, provided that the sums exist. What, Sebastian? Yep. So it might very well be, it gets a little dicey when you're thinking about things that aren't necessarily constant. Well, let me try to give you a concrete example here. We'll keep it simple. So what if I'm looking at from I to 1 to 5 again of I? What's that sum going to be? Not 5i. I'm not multiplying together. So this is the thing where it can get deceptively complicated pretty quickly. So remember, I is going to have how many values when I write out this sum? 5, right? The first value of I is going to be what? 1. So this sum is going to be 1 plus 2 plus 3 plus 4 plus 5. So this equals 15, right? So what would happen if I decided to triple all these numbers? So instead of that, I'm going to take the sum of 3i. But isn't that the same as me doing this, factoring out 3 times 1 plus 2 plus 3 plus 4 plus 5? And what I just showed you was that this 1 plus 2 plus 3 plus 4 plus 5, I can just rewrite this as the sum from 1 to 5 of I. So basically, it's kind of, this is another way to think about the distributive property. If I'm going to multiply each one of my Any questions on anything we did here? So let's go back to a finite Riemann sum for a second. So this function here over the interval 0 to 3, I want to find the Riemann sum using right endpoints and 3 subintervals. So I'm not sure I know what this function looks like. So I basically want to find this Riemann sum. So let's write it in sigma notation. From I equals 1 to what's the end value? What's our end value in this case? 3. And probably should use different numbers, but why is the answer 3 there? But the what? That's not actually why that answer is 3. So remember, the number at the top of the sigma notation here tells you how many, basically how you're partitioning. How you're partitioning your interval. So my interval goes from 0 to 3. Interval goes from 0 to 3. And I want to split it up into 3 subintervals. So the fact that I'm splitting it up into 3 subintervals is why our end value is 3. So this right here leads us to n equals 3. Now what we should do is figure out what all the components are. If I want to use equally sized intervals, what's my delta x value going to be? How'd you get 1? Yep, so each one is going to be 1 wide. And then what are my 3 values of x going to be? No, I just want the input so far. Yeah, 1, 2, and 3, right? So yeah, so my little subintervals are going to be basically this. 0, 1, 1, 2, and 2, 3. So the right end of each one of those is 1 or 2. Go ahead, Sebastian. Right. Why are we not using n? Why are we using 3 instead? Anybody else? Right. So in this case, I'm saying n is 3. So I'll highlight this again. If I want 3 subintervals, I'm telling you what the value of n is. But in this case, I know what it is. But it's not something I want or think on later. In this case, good question. All right, so this sum then is going to be three different things added together, it's going to be f of 1 times 1 plus f of 2 times 1 plus f of 3 times 1. What is f of 1? More importantly, how do you find f of 1? Yep. So -5, -4, and then 9. Oh, that's disappointing. So what does the sum end up becoming? 0. So just to highlight, if you're thinking about this in terms of area, then that should be a problem. But now we're looking at the situation where we can have things like figuratively speaking, like negative height. Sebastian,
How did you do that?
how did I get -5? Yeah, f of 1 is equal to 1 cubed minus 6 times 1. Yeah. So yeah, the function notation, I'm not doing anything new with function notation. So when I want f of 1, f of 2, and f of 3, I'm evaluating the function at those 3 x values. Daniel, do you have a question? Oh, this character right here isn't very well written. Now it's ugly, but still more readable. Any other questions? Okay, so let's do this. Let's actually find this here. We just did a Riemann sum with 3 intervals. That's not hard to do. So let's find this integral. So we're looking at a Riemann sum, essentially. I mean, soon we're getting to the point where we just think of integrals for the sake of integrals, but really, this is a Riemann sum. So let's write it like one. The limit as n goes to infinity of I equals 1 to n of f of xi star times delta x. For simplicity's sake, let's just think about all these intervals, all the little subintervals being the same length. So basically, we got to fill in the blanks here. If I'm going to evaluate this Riemann sum, I need to think about what delta x is. I need to think about how to generalize f of xi star. What's delta x going to be in general? We said it was 1 last time. Think about how we got there. I mean, it's going to be approaching 0, but let's talk about like a specific case. So like, think about a specific n. Yeah. So the length is given by the right end minus the left end, right? And how many rectangles am I going to have? And so eventually I'm going to vary n, but for now, I can think of each rectangle being 3 over ny. Let's also talk about this. Let's take a first few. Let's start with 3 of them. I'm going to say let's work with right endpoints because it's pretty easy to think that way. Rectangle. Where's the right hand of the first rectangle? It's going to be 3 over n, right? And for now, I'll say this. So it'll be the left end plus 1 rectangle width. So here's 0. This point's 3 over n. What will the next point be? 6 over n. These are just evenly spaced, right? So then what? 9 over n, and then so on. So I get 3 over n, 6 over n, 9 over n. Can I unite these and generalize them under x sub I. What is I equal to for the first one? What's I equal to for the second one? So, and then I is equal to 3, right? So is there a way I can draw like a map between, if I give you an I value, can you tell me what the x value is? I times what? I times delta x, or in this case, I'll just call it I times 3 over n. So basically, whatever the I value is, you're going to move to the right that many delta x points. Maybe it is helpful to think about it as both I times 3 over n and I times delta x. So now I think I want to rewrite this one more step like this. As n approaches infinity of, oh, I'm mixing things up. The limit as n approaches infinity of this sum, I equals 1 to n of f of 3I over n times 3 over n. Are we okay with the change I made there? Now I'm going to do one more thing just to drop the specifics about our function in there. That's going to be 3I over n cubed minus 6 times 3I over n, all times 3 over n. I'm going to pause there for a second. The rest of this is just going to be me manipulating this, but are we okay with where this expression came from? Sebastian? So from here to here? So this 3 to n, this 3 over n and this 3 over n are the same. That's just delta x. The rest of this is me applying the function. Remember that my function is x cubed minus 6x. So basically I found a recipe for x. I'm going to use that recipe and plug that into the rest of the function. Basically what I have is this: f is a function of x, but x is a function of I now. So if I keep going, how can these things be dealt with? 27I cubed over n cubed minus 18I over n times 3 over n. Uh, 27 times 3 is 81. 81I cubed over n cubed minus 54I over n squared. I think I messed something up, didn't I? Fourth. All right, I think that's good so far. But now I'm going to split these up. The limit as n approaches infinity of this sum. And actually, I'm going to pull some things out. What's the only variable? So look at the sigma notation. What is the variable as far as the sigma is concerned? I, right? So I'm going to go ahead and pull everything else out. 81 over n to the fourth times the summation notation of I cubed minus this limit. The limit as n approaches infinity of, actually, I want to pull some stuff out of there too. 54 over n squared Any questions of where I am right here? So I'm kind of stuck without knowing what those, like, do we know what happens if I add up together like all the first, if I add up the n, those n I cubes? I think I gave you those just a bit ago. Yeah, so I can go ahead and substitute those in now. And I might have to stop there and pick this up next time, but let's at least do that. What is this summation equal to if I add up together all those, the first n and I cube numbers? Someone write that down?
But it's n times n plus.
Like that, right?
Yes.
Minus 54 over n squared times, help me out again. Actually, I lied. We're going to stop. So we're almost at the end of that. We are very close to this integral along with the Riemann sum. We'll find out what the answer really is next time. I'll stick around if anybody has any questions. Otherwise, I will see you all Friday. What? I'm sorry? If you want to stick around, I'll give it to you. I'll make a note to change it.